Okay, guys, Mr. Antonucci here, and we're going to start section 6.4, applying properties of the definite integral. You can see our objectives there, and we're going to break this into 3 videos. In this video, we're going to talk about using the properties of the definite integral. In the next video, we're going to do objectives 2 and 3, where we work with the mean value theorem for integrals, as well as the average value of a function. And then in the third video, we're going to interpret integrals involving motion on a line. So these properties are going to make it a lot easier to evaluate definite integrals. The first one is basic, just the sum of two functions. So similar to with derivatives, if you're adding functions within an integral, you can integrate each one separately. Okay, so here's an example. If we have the integral from 0 to 1 of x squared e to the x, then we can just rewrite this as the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of e to the x dx, which the antiderivative of x squared is x cubed over 3. We're going to evaluate that from 0 to 1. And then we would add the antiderivative of e to the x is itself. We're going to go from 0 to 1. So if we plug in 1, that's going to give us 1/3 minus plugging in 0 would give us 0 plus e minus 1. Okay, and then if we put that all together, you would end up with e minus 2/3 as the exact answer for that one. Okay, and typically you're going to want to write the exact answer unless it says round your answer to 3 decimal places or something like that. The next one is a constant times a function. Similar to derivatives, if you have a constant times a function, you can factor the constant outside of the integral. So for this one, you have the integral of 1 to e of 3 over x. That 3 shouldn't have been there. But we could factor the 3 out, and you have 1 to e of 1 over x. The x doesn't come up to the numerator or anything like that. Sometimes students accidentally do something like that if they're factoring the numerator 3 out. But the antiderivative of 1 over x is natural log absolute value of x. And the 3 is going to multiply that, and then you'd have from 1 to e, which is going to be 3 times the natural log of e minus the natural log of 1, which is 3 times 1 minus 0, which gives us 3. Okie doke. All right. Next property is suppose each of the functions 1, 2, 3, function 1, 2, 3, and so forth. Then this is basically just the repeated application of the sum and difference properties with the constant multiple property. So we're going to kind of combine things and do a lot of work here to solve this property, or excuse me, solve this problem number 3. Now, for this definite integral, there is no like reverse quotient rule, so to speak, even though we have a quotient here. So lots of times it's helpful if you try to simplify the integrand, especially in a situation like this. So one thing to note is that this function for the integrand is continuous on the interval 1 to 2, because the only value that would make it undefined is when x is 0, and that is not on the interval that the integral has for the limit, so the interval 1 to 2. So if you divide each of the terms by 2x, you would end up with 3 halves x squared minus 3x minus 5 halves plus 2 over x dx. All right, so all we did was algebraically simplify that expression, okay, or the integrand. So then that would be the integral from 1 to 2 of 3 halves x squared dx minus 3 times the integral from 1 to 2 of x dx minus 5 halves times the integral from 1 to 2 of just dx. Now, if it helps to put a 1 in there, that might be suitable for you. And then plus 2 times the integral from 1 to 2 of 1 over x dx. Then we just anti-differentiate each of these and evaluate. So this would be 3 halves times x cubed over 3 evaluated from 1 to 2. And now the 3's would cancel. You'd really have x cubed over 2 minus 3 times x squared over 2 evaluated from 1 to 2 minus 5 halves times x evaluated from 1 to 2 plus 2 times the natural log absolute value of x evaluated from 1 to 2. Okie doke. So in that first set there, you're going to have 1 half, because the 3's cancel, times 2 cubed, which is 8, minus 1 cubed, which is 1, minus 3 times 2 squared over 2, which is 4 divided by 2, which is 2. And then plugging in 1, you would have minus 1 half. Then minus 5 halves times, plugging in 2 and 1 and subtract to just x, you would have 2 minus 1, plus 2 times natural log of 2 minus natural log of 1. Okay, now if you do all the subtraction there and distribute and combine like terms, you'll end up with 7 halves, negative 7 halves rather, plus 2 natural log 2. Okay, now one of the things that you could actually do with this is if you just had this basic integral, 1 to 2, of 3 halves x squared minus 3x minus 5 halves plus 2 over x. I'm not going to redo the whole thing, but usually like this middle step where you break it apart is often not included. You just do each term. So for example, you would have x cubed over 3, but it would multiply the 3 halves and it would just simplify to 1 half x cubed minus 3 halves x squared minus 5 halves x plus natural log 2 natural log absolute value of x. And then you would evaluate that whole expression there at 2, evaluate the whole expression at 1, and then subtract. You'll get the same answer, but it may reduce the amount of work that you're doing in the complexity of how it seems to be more complex. The next theorem we're going to look at basically says that a definite integral of a function from a to b can be evaluated in pieces. So if you have the integral from a to b, which represents the area under the graph of f from a to b, you could think of it as the sum of 2 subintervals. Okay, this property can be helpful, and you can actually extend this to adding multiple integrals. So, for example, in part A, if f is integrable on the closed interval 2 to 7, then we could rewrite this as you could pick any number between 2 and 7, but you could rewrite it as the integral from 4 to 2 of f of x dx plus the integral from 4 to 7 of f of x dx. Now, you don't just normally arbitrarily do this, but this property is actually necessary for that. Now, if g is integrable on the closed interval 3 to 25, then the integral from 3 to 10, you could rewrite that, or it could come about as the integral from 3 to 25 of g of x dx plus the integral of 25 to 10 of g of x dx. Okay? So this part B illustrates that that number that you break apart the integral at does not have to lie between the endpoints A and B. Okay? So now we're going to use property 4 to find the area under the graph of a piecewise defined function. So here f is x squared from 0 to 10, and it's 100 from 10 to 15. And then we want to find the area under the graph from 0 to 15. So to do this, we want the area is equal to the integral from 0 to 15 of f of x dx, which, because it's a piecewise defined function, we can do the integral in pieces. So the integral from 0 to 10 of the x squared part plus the integral from 10 to 15 of the 100 part. And now this is going to be 1/3 x cubed, evaluated from 0 to 10, plus 100x, evaluated from 10 to 15. Now be careful here. Since the limits are different on the two integrals, you can't just do 1/3 x cubed plus 100x and evaluated it at, one number and the other number and subtract. So if we keep going here, then you would have, plugging in 10, you'd have 1,000 over 3 minus 0 plus 1,500 minus 1,000. And this is going to give you 2,500 over 3, which is approximately 833.333 repeating square units. Okay, so that's how you would do that. And graphically speaking, what we just figured out was the area under the graph from 0 to 15, and we split it into two chunks. This area was right here, and this area was figured out right there. All right, now part of the definition of what it means for a function to be integrable is that it can contain a finite number of points of discontinuity. So if a function is bounded, meaning it doesn't like go off to infinity, and has at most a finite number of points of discontinuity on a closed interval, then we can find the definite integral. So for this situation, if we want to find the integral from -1 to 4 of f of x dx, where f is this crazy piecewise function, and if we go from -1 to 4, we're getting the area of all of this. Okay? So even though there is a removable discontinuity at x equals 2 and a jump discontinuity at x equals 0, we can still do this by breaking the integral up into subsections. Okay, so the first interval is going to go from -1 to 0, and that's e to the x. And then the next section is going to go from 0 to 2, and that would be x plus 3. And then the next section is going to go from 2 to 4, and that would be of the line -2x plus 9. Now, even though that there is a removable discontinuity or a hole in the graph there, that's not going to have any bearing on the area under the curve for this problem. Okay, so then we're going to anti-differentiate, plug in, and subtract. So the antiderivative of e to the x is itself. We're going to evaluate that at -1 and 0. Plus the antiderivative of x plus 3 would be 1/2 x squared plus 3x, evaluated at 2 and 0. Plus the antiderivative of -2x plus 9 is going to be -x squared over 2, but the 2 multiplies the -2 and just cancels to a negative, plus 9x, evaluated at 2 and 4. So here we're going to have e to the 0 minus e to the -1, plus, if we plug in 2 and 0, 2 squared is 4 times 1/2 is 2, so it'd be 2 plus 6 minus plugging in 0 would give us 0. And then plus, if we plug in 4, you would have -16 plus 36 minus the function evaluated at 2, which, or excuse me, minus, which is going to be -4 plus 18. Okay, now if we simplify this, add all of this up, it's going to simplify down to 15 minus 1 over e. Again, you could rewrite that 1 over e. You could rewrite that in decimal form but we're not going to do that here. All right, another theorem is called the bounds on an integral. If a function f is continuous on an interval ab, and little m and capital M denote the absolute minimum and the absolute maximum value of the function on the interval, then the definite integral has to be between the maximum and minimum multiplied by the width of the interval. In other words, if the function never dips below a certain value and never goes above another certain value, then the area under the curve has to be greater than the rectangle that lies below the curve the whole time. And it has to be less than a rectangle the area of a rectangle that lies above the curve the whole time. Okay, so for part A here, for this one, we want to find an upper and lower bound for the area of a graph of sine x from 0 to pi. All right, so the sine function, f of x here in this case, is between 1 and 0. Okay, so the integral from 0 to pi of f of x dx has to be less than or equal to 1 times b minus a, so pi minus 0, but greater than or equal to the least value, which would be 0 times pi minus 0. Okay? Now, that means that the integral from 0 to pi of f of x, which is sine x, has to be less than or equal to pi, but greater than or equal to 0. All right? So that just gives us a range of possible values to know if we're in the right ballpark when we actually get the answer. So B, for part B, we're going to get the actual area under the curve. So the integral from 0 to pi of sine x dx. The antiderivative of sine is negative cosine. We're going to evaluate at 0 and pi and subtract. So negative cosine of pi minus negative cosine of 0. All right, cosine of pi is negative 1, but you're multiplying by a negative, so it'd be 1. Minus a negative cosine is going to give you plus, and cosine of 0 is 1. So our answer is 2. That means the area of this region is 2. And notice that 2 is between 0 and pi. All right. Well, guys, that's it for this video. Hope that was helpful to you. Please reach out if you have any questions. Take care.